Hi, everyone. Thanks for joining me with this talk today. Unfortunately, I can't be there live with you today because by the time you're listening to this, I will have just gotten off a plane. But I am nonetheless excited to tell you about some work that me and a couple others in the DAS lab have been doing about predicting sequence dropout in chemical mapping experiments. So as a quick introduction of who I am, I'm a PhD student here at Stanford. I am a mathematician by trade, and that's my home department, but I try to put my skills to use doing machine learning and RNA biology with the DAS lab. So sequence dropout is a problem that we've been facing as we try to scale up our chemical mapping experiments, where the quality of our data seems to just go down and down. And I will give a quick explanation of what that looks like by doing an overview of how this chemical mapping process works, which you may have heard before, but I'll highlight some important points. So in chemical mapping, we want to understand the structure of a certain structured RNA. And the way we do that is we take many copies of our RNA and we mix it in with some probing reagent, which is going to react with certain bases in the RNA. When it reacts with them, it's going to modify them, and there will now be a modified base at that position. But the way in which it reacts depends on the local structure of the RNA. So so nucleotides that are unpaired are generally much more likely to be modified by this probing reagent than nucleotides that are paired. And so, for example, the probing locations will correlate much more highly with loops than with stems. And if we want to then figure out where this probing has occurred, we can take our RNA that's been mixed in with the probing reagent and we can sequence it. And when we sequence it, what happens is the reverse transcriptase goes backwards through the RNA until it hits one of these modified bases. And one of a couple of things can happen. Either it falls off and the sequencing read ends there, or it puts in a mutation, an insertion, or a deletion. No matter what the case is, we can align these sequencing reads to the original RNA of interest, and that'll tell us the locations of these mutations and the locations of where the RT fell off, which correspondingly are the locations where the probing reagent has reacted. And so if we look at the distribution of where these modifications have occurred, we get a distribution of these modifications across the entire sequence, which is, in essence, the chemical mapping profile, or the reactivity profile. Now, doing so requires many different sequencing reads for the same molecule. The reason is that even if there are many exposed bases in your RNA of interest, it doesn't react to all of them in a given molecule. In general, only 1 to 2% of the bases will actually have any modification at all for a given sequencing read. So for this reason, we need to collect many copies, many different sequencing reads for the same molecule to get any kind of good signal on what the underlying probing distribution is. The number to keep in mind is 500. 500 generally corresponds to a signal to noise of 1, and below 500, we're getting to the point where the data is less and less useful. Now, of course, when we do a chemical mapping experiment, we don't just do it for one RNA, we can do it for many at once, thousands, and recently with RibonazaNet, millions of RNAs. But it's all done as one big experiment. And at the end, the reads are aligned to the original library that you synthesized in the first place. And what you see is that some of the RNA sequences from your original library have a whole bunch of reads aligned to them. And some of the sequences, usually most of the sequences, have very few reads aligned to them. And this means that most of the data in our chemical mapping experiments is not useful to us because there's just not enough aligned reads to tell us where the distribution of where these probing reagents would have reacted. And let me show you some data from two of our recent experiments. On the left, we have the test set from RibonazaNet, and on the right we have OpenOp 4 and 5, which was one of the recent Eterna challenges. And this is a histogram of the number of aligned reads that each sequence got. Now, in red, I've plotted the signal-to-noise threshold of 500 that I indicated, and we see in both cases the vast majority of sequences end up with a number of aligned reads below, and in many cases far below, the signal-to-noise threshold, with this characteristic spike of many sequences getting 0 or 1 aligned reads. And at that point, that data is completely useless to us. We can't do anything with it at all, because either there's no data or one read doesn't tell us anything about the underlying structure. And for this reason, because we've been seeing this occurring more and more in our recent experiments, late last year, Riju tasked me with trying to understand how can we predict what makes this happen. So we're getting all of these sequences from Eterna players and other contributors, and it's not clear which of them are actually going to give good yield, high yield data, and which of them are going to end up in the completely useless section. And so when he gave me this task, the first thing that I did was I just looked at the sequences on either end of the spectrum. And after I looked for a while, I found these two sequences, which really highlighted how difficult this problem is going to be. So these are two sequences from the test set of RibonazaNet. They are only 8 mutations apart, so they're very similar in sequence, but the mutations are also compensatory mutations. So the predicted structure, predicted secondary structure, is actually the same for both of these sequences. And yet, as you can see, the number of aligned reads that each of these sequences got at the end of the chemical mapping experiment is vastly different by 2 orders of magnitude. So what this says to me is that there is some deep, intricate, and difficult to non-obvious relationship between the sequence, the structure, and the number of reads that we'll end up with at the end of the chemical mapping experiment. And so the natural way to model this is with deep learning. And so that was the approach I used to try and model this task of sequence dropout. The most successful approach was to take a copy of RibonazaNet, which by the time you're listening to this, Shujin will have already given his talk, so I won't go into detail about that, but to take a copy of RibonazaNet and fine-tune it for the task of predicting the aligned read counts for each sequence. Now, the main change that needs to be done is RibonazaNet predicts a one-dimensional feature, which is the chemical mapping profile, but I needed to predict a zero-dimensional feature, which is the read count. And so all that's really different about RibonazaNet-Drop is that we take the predicted features output by RibonazaNet, and we take the mean over the sequence dimension, and that gives us a single number, or 2, depending on if you want 283 and DMS. Now, of course, this can give us positive or negative numbers, and we only want positive. But if you interpret these as log reads instead of traditional reads, then that doesn't matter. And in fact, this ended up being useful for training. If you try and train it on the read counts themselves, then what you find is the training doesn't converge. And the hypothesis there is that the read counts just span way too big of a scale, 6 orders of magnitude, for the model to correctly predict. But if you work in log read space, they only span from 0 to 6, like the values of 0 to 6. And so that the training ended up working much better if you work in log space. So the actual data that was used is the same trained data from RibonazaNet, except instead of the chemical mapping profiles, we trained it on the read counts. 70% of the data was for training, the rest we used for validation. And important to keep in mind was that all the sequences used were 177 MERP. And so the model has only seen sequences of length 177 during training. And I will say there were a couple of other models that I tried. The main other one that seemed to be successful was an LSTM, so a completely different architecture, and trained from scratch, so not fine-tuned on any chemical mapping data. And this seemed to have comparable performance, but the difference is that this needed to be given as input the secondary structure as well as the sequence. And RibonazaNet-Drop was able to achieve better performance than this LSTM while also not requiring any secondary structure as input. So how does it do at predicting the read counts? Well, the first thing we tested was on the test set for RiboNanza, and that's what I've got on the left. This is a histogram of the differences in the log counts of the reads. And we see that it can get within 1 to 2 orders of magnitude, usually within 1 order of magnitude, which is not perfect, but it could be usable for predicting which are going to be the high yield sequences and which are going to be the low yield sequences. But what's more important is this correlation of 0.8. And this is indicating that it is indeed learning something about how the sequence and potentially the structure relates to the yield that corresponding sequence will get at the end of the experiment. And on the right, I tested it on another data set, positive 240, which contains some very intricate pseudoknots that have a length of up to 307, so longer than what it's seen during training. And it actually ends up with a higher correlation than on the test set for RiboNanza, but I think that it's because this is actually an easy data set to predict the reads for. You can predict it with much simpler heuristics like longer stem length. But this at least indicates that RibonazaNet-Drop is also picking up on these underlying heuristics that may potentially guide the yield of the sequences. A third data set that I tested it on was positives 390. Now we're getting to sequences up to 457 nucleotides, so much longer than it saw during training. And the correlation has gone down and the histogram has shifted. It's now seeming to overestimate the number of reads for each sequence. And because of this, I had the idea that maybe because these sequences are longer, the reads are going to be lower. And what if we just renormalize by the ratio of the sequence lengths? So you can also take these predictions and renormalize by the ratio of the sequences that saw during training versus the sequences in this set itself. And this centers the distribution. Of course, it doesn't change the correlation, but the correlation is still much better than random chance. Okay, so we have a model that can somewhat successfully predict which sequences are going to be useful to us for chemical mapping and which sequences are going to be useless to us. The next question is what we can do with it. So I've kind of alluded to this already, but the first thing we can do is we can look at our library and we can, before we do any experiments, pass the entire library through RibonazaNet-Drop, look at the predicted reads, and then take all the sequences with the read count below a certain threshold and just throw them out. And so this is the idea that we have to pay to synthesize these, we have to pay for the sequencing costs, and yet at the end of the day, we're not going to get any quality data on them. So this is one option to try and improve the library using such a model. This can also happen at the level of the Eterna player. So if an Eterna player wants to submit designs, they can pass their sequences through RibonazaNet-Drop, and they will get some idea of which of the designs are more likely to give high quality data and which of the sequences are less likely to. A second method that could be used to increase the yield if we have such a model is to take our library and to split it into 2 or more libraries depending on the read counts. So in this simple example here, you would split it into a library containing all the low yield sequences and another library consisting of all the high yield sequences. And there's a method for doing this. You can attach before synthesis these primers, dial out primers, which can then separate out the libraries via PCR. And what you could do with this is you can then process the 2 libraries independently. The school of thought there is that the high yield sequences now will not crowd out the low yield sequences. And so the low yield sequences will hopefully end up with a higher number of overall reads. So we wanted a blind test for all of this. Firstly, a blind test for RibonazaNet-Drop's performance, and also a test of that idea I mentioned of splitting the library into multiple sub-libraries. And a good candidate for this was the OpenOpt 4 and 5 challenge, plus some extra sequences from external contributors. And we passed the entire library through RibonazaNet-Drop, and using the predicted read counts, we split it into 3 sub-libraries, one sub-library containing all the lowest read sequences, one sub-library containing the medium read sequences, and one sub-library containing the high yield sequences. And as a 4th experiment for a control, we also did the same experiments, but without any of this splitting, any of this pooling at all. So the first thing I'll show you is how does RibonazaNet-Drop actually perform on predicting the read count for OpenOpt 4 and 5. Here is the histogram, and we see the correlation is lower than any of the other data sets we've seen so far. So that's not great, but maybe it's good enough for us. Because for this experiment, we don't need the actual perfect read count for each sequence. We just need to know which of the 3 subpools should it be put in. Should it be put in the low, the medium, or the high subpool? And so what I've put here is a confusion matrix. On the x-axis is which pool did RibonazaNet-Drop predict the sequence should be put in, and on the y-axis is which pool should the sequence actually have been put in based on the actual experimental read counts. And we see that in general, a sequence is more likely to be put in the correct pool than in an incorrect pool, at least for low and high. For medium, it is still more likely to be put in the correct pool, but compared to the other 2, but not compared to all 3 pools. But something to note here is that the low read sequences are much more likely to be put in the low read pool than the high read pool, and the high read sequences are much more likely to be put in the high read pool than the low read pool. So even if RibonazaNet-Drop isn't perfect, it's still pretty good at separating out the very worst sequences from the very best sequences and putting them into 2 separate sublibraries. So what effect does this actually have on the read count when we do this pooling step before experimentation? Here are some statistics. In the first table, we see when we introduce this splitting into 3 subpools, the mean number of reads for the entire library jumps by a factor of 2. The median number of reads jumps by a factor of 4, and the total dropout, which I'm using to refer to the number of sequences that got 0 reads, so not a single piece of data was collected for them, significantly decreases from 2000 to 350-ish. And this is very good evidence that this technique of splitting up the sequences into individual subpools does indeed provide a boost to the yield, and also that RibonazaNet-Drop is sufficiently capable of predicting reads for it to be used for this purpose. And in the second table, I've put how the read counts change for the individual pools. So the low and medium read pools, we see a big jump in the number of reads when we introduce the subpooling. Kind of paradoxically, the high read sequences decrease their yield when we introduce pooling. There is an explanation for this. It turns out the dial-out primer that we use to separate out the high yield sequences from the entire library had some issues with crosstalk, and so there were issues in separating out the library from the sub-library from the whole library. And so this is the explanation as to why the read count actually went down. But ignoring that factor, we do see that the pooling has a significant impact on the overall read counts. And I'm showing here histograms of the read counts. On the left is one of the histograms I showed at the beginning. And on the right is the histogram for the same library, but now we've split it up into 3 subpools. And we see that the big spike at 0 or 1 reads has significantly reduced, and the number of sequences that is above the signal to noise threshold has also increased by a fair amount as well. Now that experiment, while it did increase the number of reads significantly, it had its own issues of the 2A3 reactivity was very low, essentially zero. And so even though it was good that we saw the reads increased, it was not usable as data on the 2A3 reactivity. And figuring out why was a task that Riju and Anne from our lab undertook for a while. And eventually they solved it. And so this is data that Riju collected just this week with the 2A3 reactivity rescued back to normal levels. And I'm just showing this to show that on this rescued data, RibonazaNet-Drop also has comparable performance on the predicting the read counts and in splitting it into the 3 subpools. In fact, it actually seems to do a little bit better, but it's hard to say if that's anything significant. And I will highlight another thing that RibonazaNet-Drop was able to correctly predict, which is something that was noticed by Eterna players a while ago, is that as you increase the number of GC pairs in the barcode, the mean reads for that sequence decreases in a pretty significant way. And on the left, I've shown that this trend does indeed exist in this OpenOt 4-on-5 dataset. And on the right, I've shown the same trend, but using the predicted reads from RibonazaNet-Drop instead of the experimental reads. And we see that RibonazaNet-Drop is able to recapitulate this trend of decreasing read as we have increasing GC pairs, showing that it is indeed understanding something about the relationship between sequence and read count. And so this demonstrates that it can understand these trends well. And so this is something to keep in mind if you are going to use RibonazaNet-Drop, which is that the absolute numbers in RibonazaNet-Drop don't mean so much. It won't necessarily get the absolute numbers correct, but the trends, it's much better at getting correct. And on average, it will get the correct number of reads. So it's much better predicting relative reads, so comparing the reads between sequences and trends, than predicting absolute reads. And something we also saw is that for very long sequences, like in positives 390, it struggles to correctly predict the reads, although renormalizing it by the factor of the ratio of the lengths did seem to help. So of course, the question is then how can you use it? The easiest way to actually get started with using RibonazaNet-Drop is with the Kaggle notebook. And hopefully at this point, Riju will paste the links to both of these places in the chat. And so the Kaggle notebook, everything is set up. You just need to put in the sequences and it will spit out the predicted recounts. That's good for small runs. If you want to tinker with it yourself, if you want to run it locally, or if you have a very big run that you wanted to do, you can also clone the GitHub repository and run it locally. And there's instructions in there on exactly how to do that. And I will finish out by mentioning that there are multiple further tests of RibonazaNet-Drop ongoing. The first one is we're redoing OpenOt 4-on-5 with subpooling, but using a different technique. So originally the technique was to split it into 3 subpools and process each subpool independently. This was shown to work, but the issue is this increases the number of experiments we have to do by 3-fold, which is not great. And so what's being tested now is we split up these sequences into subpools, but then we mix them back together again in ratios that depend on the mean reads in each of the libraries. So in this small example here, we would mix the sequences in the ratio 26:1. And another test that is ongoing as well is RiboNanza 2. So this is scaling up to 8 million sequences, and it's being subpooled into 2 pools, each of 4 million sequences. And this is using the same technique of remixing at varying ratios. So I'd like to thank everyone who helped me out on this project, especially Jill, Rachel, Ray, and Riju. And I'd also like to thank all of you for listening.